Let's start the lecture then. The topic of today's lecture, the first part of the lecture, is called the peculiarities of radiation absorption of energy by atoms and molecules. A very voluminous topic, so we choose from this topic exclusively what you will work with directly in the laboratory work that has already begun this week. Namely, we will consider such phenomena as light absorption, light scattering, and light polarization. So two presentations of the first presentation are the first three questions here, but this is probably the shortest part. And the second part of the lecture is the polarization of light. Difficult and very voluminous material. So, the ideas about light, about what light is, changed according to the types of scientific revolutions. The first revolution, I beg your pardon, the first revolution, the so-called Aristotelian revolution, is due to the fact that science separated from other forms of knowledge of the world, that is, from sensory knowledge of the world, from other types, and began to represent a separate direction of studying the world, well, or knowledge of the world, in about the 4th century BC. Before the second scientific revolution, please note, it took 2 whole millennia. That is, 200 years passed before the next revolution. Just a second. This is the 16th century. The starting point for the Newtonian revolution. And this revolution is marked by the fact that such a stable mechanistic picture of the world appears, and the basis for the appearance of this picture of the world is already experimental and mathematical knowledge. The third stage of the revolution, the third, or rather the scientific revolution, the Einstein revolution. The interval between the Newtonian-Einstein revolution is only 1 century, that is, the acquisition and processing of scientific knowledge accelerated, and in particular, this meant the following. During the Einstein revolution, the structures of the atom, the phenomenon of radioactivity, and the discreteness of the nature of electromagnetic radiation were discovered. Other discoveries, they of course, also contributed to scientific and technological progress, thanks to which we now enjoy many and many benefits of civilization, in particular, thanks to the study, understanding, and use of the very complex structure of the atom, the phenomenon of radioactivity, properties of electromagnetic radiation. Despite the fact that the gap between these revolutions was small, there was a time interval of 1 century. The qualitative leap was due to the fact that humanity abandoned the mechanistic picture of the world. And the conviction that all natural phenomena can be explained with the help of equations was undermined in general. During the Einstein revolution, we get the idea that a number of regularities are probabilistic in nature. That is, statistical regularities appear in many physical laws, including to date, the wave-particle dualism of light, that is, the theory that was proposed during the Newtonian revolution. The theory that light is both a particle and a wave, and can in some cases behave like a particle stream, in other cases behave like a wave. This wave-particle dualism, it was confirmed just in the third revolution, although before that light was considered by different researchers, and there were confirmations of this as a stream of particles or a particle. Yes, Newton himself in particular was an adherent of this theory, and, well, at about the same time with him, the light of the Jugens was considered as a wave process. To date, the dual nature of light has been confirmed, and the further development of quantum mechanics has only confirmed de Broglie's hypothesis. At present, the corpuscular and wave approach are simply different technical representations within the framework of a holistic theory of this dual theory. Well, to simplify, we will understand light in various phenomena, mainly in the form of a stream of particles. For example, during absorption, during interaction with a number of substances, during radiation, that is, when light is emitted by atoms, and in a number of other phenomena, such as interference, diffraction, polarization in particular, which we study today. Light is mainly considered like a wave. Here are the difficulties. So, the first phenomenon that we are considering is called light absorption. So you have a container depicted in front of you, well, or some kind of vessel with a liquid transparent to light, with a letter and 0, well, and the arrow is red, respectively. The luminous flux falling on a vessel with a liquid, and with index 1, is the intensity of the light that has passed through the substance. Well, that is, through the vessel, through the liquid that fills this vessel. Well, accordingly, the ratio between the intensity of light incident on a substance and passed through a substance establishes the laws of this phenomenon, the laws of light absorption. Well, by absorption, it simply means a decrease in the intensity of light when passing through a substance, due to the conversion of light energy into other types of internal energy. In other words, this part of the light energy remains in the substance, turning into thermal energy in this substance, into heating, for example, under the action of light, photochemical, that is, conversion chemically under the action of light, and other kinds of energy. The basic laws of light absorption are Bouguer's law and Lambert-Beer's-Bouguer's law. In other words, this topic has been consistently studied, the phenomenon of light absorption. And so Lambert and Baer added their research to Bugger's law. Bugger's law is formulated for so-called homogeneous media. Simple environments. The absorption coefficient K is set with a minus sign. L is going back to the previous slide. That is, L is the thickness of the absorbing layer. Well, the absorption coefficient characterizes the very vessel, that, more precisely, the liquid that fills the vessel. In other words, the greater the thickness of the absorbing layer, the greater the absorption coefficient, the weaker the light flux at the output. The connection between the incident light and the light that has passed through the substance is here. And zero is what falls on the substance with which the luminous flux interacts in the future, but simply this is what has passed, or what remains after interacting with this transparent translucent substance. In general, the ratio between falling and past is exponential. That is, e to the degree of minus, well, that is, whatever the thickness, e to the degree of minus, will only give a decrease in the intensity of light that has passed through the substance. Lambert-Baer's Burger law has already been formulated for concentrated solutions, i.e. complex solutions, having some kind of homogeneous solvent and plus molecules of some substance. The size of these molecules, the composition of these molecules, and their ability to interact with photons of light is calculated through the paint absorption index. Here is the letter Ch denoted by the paint absorption index. C is the concentration from that main absorbing substance. Well, if we are talking, for example, about blood, then the blood plasma will be the solvent there, and the shaped elements, red blood cells, should be characterized both through concentration and through the paint indicator of light absorption, that is, the ability to interact with the light flux. The essence of the law is the same. In other words, it is an exponential relationship between the flow of incident light and the flow of light that has passed through this absorbing medium. Just keep in mind, I'll go back to the previous slide again. The substance with which the color interacts must be transparent or translucent to light, because substances that completely absorb the color flow will not give an opportunity to study such a phenomenon. And for use, of course, for some experiments. The next phenomenon we are considering is called light scattering. Unlike light absorption, the process of light scattering is caused by spatial redistribution of the luminous flux. Look, the definition of light scattering is formulated in the same way as the definition of light absorption. In other words, both refer to the processes of reducing the intensity of light when passing through a substance, but the reason for the absorption of light is the transformation of energy. The energy of light turns into heat, into chemical processes, and other things. And when light is scattered, the intensity of the transmitted light decreases due to the redistribution of the luminous flux in space. That is, here on the intensity of the light flux incident on the substance, but the light intensity here, by the way, is not very obvious, an obvious pattern. Here the intensity of this light, it should certainly be weaker. Well, here is another drawing as an example. It can be seen here that the process of light scattering is accompanied by a decrease in light intensity. That is, the closer the light is to the light source, the brighter the beam. The further away, the weaker the beam. The intensity of this light is weaker, but what we see on the screen, or in this case, probably on some surface, is already, well, special technical effects. In other words, light scattering is based on two phenomena. This is the ability of light to be reflected, depending on the angle of incidence. The proportion of reflected light can vary, and the ability of light to be refracted. That is, having reached another medium, having reached the boundary of the media, the light changes its direction of movement. It is customary to distinguish three main patterns in the scattering of light. These are the patterns that Rayleigh was engaged in, which the scientist Mee and Tyndall were engaged in. In other words, Rayleigh studied scattering on small particles in detail, or practically on homogeneous media. And it was thanks to his research that it became obvious why blue light scatters much more strongly than red. This is due to the shorter wavelength. Scattering is scattering on large particles present there in suspension or in a solvent, and Tyndall scattering. Unlike Rayleigh scattering, Tyndall scattering considers the behavior of light in colloidal solutions or suspensions. That is, what is more often used in medicine. Another feature of the media that Tyndall dealt with is the presence of Brownian motion of these inhomogeneous media. The pattern that Rayleigh established, it is, well, in some way true for Tyndall scattering. Without going into details, let's note only the main points. So, does the scattering of the relay include such light scattering? In which the wavelength, well, more precisely, light interacts with particles whose dimensions are smaller than the wavelength of the incident light. In other words, this uniformity is due to the fact that the particle sizes are small. Further to new, as an example of scattering, the phenomenon of relay scattering, scattering on turbid media, can be given. Smoke, fog, something that can be observed firsthand. Next, with Rayleigh scattering, the state of the medium does not change. The intensity of the scattered light. Here it is this value, according to Rayleigh, inversely proportional to the fourth power of the wavelength. Well, that is, you can write minus the fourth degree, you can write a unit divided by lambda in the fourth. Here it is a significant difference in the scattering of red and blue light sources, well, or light rays. That is, all warning lights, stop lights are made of red glass in order to reduce the proportion of light scattering. In other words, red light, as a carrier of a longer wavelength, does not dissipate as quickly, that is, not as intensively as, for example, blue. So, let's move on to the next phenomenon. This phenomenon is called the polarization of light. Well, before we move on to polarization, I'll just add that the Tyndall phenomenon is characterized by approximately the same pattern, but it is Tyndall scattering that allows doctors to actively use these phenomena. Optical methods for determining the size, shape, and concentration of colloidal particles and some macromolecules are based on the Tyndall effect. In laboratory work, you will study the phenomenon, mainly the absorption of light, on a device called a photoelectrocalorimeter. So, well, the second part of the lecture is the polarization of light. Do you see the presentation? Yeah. All right. So, with the phenomenon of light polarization, you will also work in laboratory work. That's all that is connected with the word polarization, polarimeters, polaroids. Everything is based on, well, those patterns that we are going to talk about now. I warn you right away that the duration of the lectures, this part of the lecture, it probably will not exceed 30 minutes. So write if you don't mind. Let's try to finish the lecture in half an hour without a break, as he looks at it. Well, I see a few responses, then let's continue. Well, in terms of this lecture, of course, the basic concepts. Methods of obtaining polarized light patterns reflecting the behavior of polarized light, the phenomenon on which the use of polarized light for biomedical research is based, and the main directions of using polarized light. Part of the slides you see can be called a repetition of what I have already said. In other words, in the case of interference polarization, we consider light as primarily an electromagnetic wave. The wave, forgetting its corpuscular nature, and in particular, when we characterize the phenomenon of polarization of light, we say that light is an electromagnetic wave with a wavelength there from 380 to 780 nanometers. Well, light is what is perceived by that area of electromagnetic waves that is perceived by the human eye. Sometimes the concept of light includes nearby areas, that is, infrared radiation and ultraviolet radiation, despite the fact that these ranges are not fixed by the human eye. So, here is an image, a schematic representation of the very electromagnetic wave that we believe can emit a single atom. That is, a single atom, being a light source, emits an electromagnetic wave. There are two components in an electromagnetic wave. This is the electrical component. Here it is depicted in the plane of our screens in yellow. And the second component is the magnetic tension. In this case, perpendicular to me, for example, the plane of the table, that is, it coincides with the plane of the table. First of all, perpendicular to the plane of which the electric voltage vector oscillates. That is, the 90-degree angle between them is always preserved. Well, it's true that this angle is turned, you see, in this case in our direction, at the next moment of time, from us these 90 degrees and so on. So, a separate atom will give exactly this layout. That is, the E vector of electrical tension will oscillate in one plane. The magnetic intensity vector will always be perpendicular to the oscillations of the electric vector. Here is another picture that shows that with respect to the direction of propagation, these vibrations do not change the space of a single atom. And if it would be possible to depict a ray of light in this direction, then the red arrows are the electrical component, the blue arrows are the magnetic component of the vibrations of an individual atom. Well, since the light sources that surround us are a collection of a huge number of atoms, simultaneously emitting electromagnetic waves at the same moment, then, of course, a set of vibrations like this, if they could be depicted as separate lines. Well, that is, here is one single line, this is one plane that oscillates, let's say, the electric voltage vector with arrows. Another line, another direction. And it turns out that the light with which we most often interact is light from any heated sources, starting from fire and ending with the sun. This is the so-called natural light, in which the direction of the electric voltage vectors are different. Well, it is customary to depict here in the form of such a dandelion. In the resulting wave, we present the following picture. The electric tension vector randomly changes its orientation in time. On average, it turns out that any of these directions, like this arrow, is equal. This natural light can be called a nonpolarized color. That is, if there is a light source somewhere in the distance relative to this point, relative to the center, where I am pointing with a helmet. For example, there is an incandescent bulb, an ordinary incandescent bulb, then the electric vectors that could be fixed will disperse in such equal directions in the case of a natural light source. If the light source is even a phone, for example, our phone, that is, not a heated device or light reflected from some surfaces, then we will no longer see such a picture with the same, well, approximately or statistically the same long vectors. We can see fully polarized light, that is, when the direction of the electric voltage vector is allowed only in one plane. Well, such an ideal picture. It is possible in the case when the light source is one atom, or in the case when we have made many atoms oscillate in one phase, with one intensity. Most often it is possible to deal with partially polarized light. Imagining partially polarized light, we must keep in mind that such a strict polarization is impossible for many atoms emitting certain wavelengths. But to get, as it were, a preferential oscillation, coinciding with one or another plane, is an affordable matter. The peculiarity of polarized light is that with the help of vision, a person does not distinguish natural light, polarized light. The very process of isolating polarized light from natural light is called polarization. And accordingly, devices that work with polarized light and are able to take measurements of this polarized light are called polarimeters. In laboratory work, as I have already said, you will have to have a body with a polarimeter, which is designed to measure the concentration of sugar. The work is called saccharimetry. There are several definitions concerning this vector E and the vector ash. That is, if you want, you can call the plane of oscillation of the electric voltage vector. This is the yellow component of the electromagnetic wave. But here is that plane, that is, the plane of the screen in this case. It will be called the plane of polarization. In other words, the polarization process is determined by the behavior of the electric intensity vector. For physicians and biologists, behavior is also more important, studying the behavior of vector E because, look, in the processes of interaction of light with matter, both chemical, biological, and physiological, that is, in the interaction of light, Even with the retina of the eye, the electrical component of the electromagnetic wave plays a major role. That is, not a magnetic, but an electrical component. Therefore, this vector E vector, which describes vibrations or sets vibrations in this plane, is also called a light vector. Well, although the electromagnetic wave is something inseparable, that's at least how we should imagine it. There are several ways to obtain polarized light. These are polarization at reflection refraction of light and polarization at double ray refraction. So the color natural light, that is, the light from a flashlight, from a light bulb, the focused light directed, there can be polarized when the beam is directed at the interface of two dielectrics, that is, media that do not conduct an electric current. The light reflected from the interface and the light refracted in the second medium, in the second electric, they will have different degrees of polarization. You see, when reflected, almost 100% polarization is observed here, and the refracted light is transformed into partially polarized light. Polarization with double ray refraction is polarization, which we will talk about in a little more detail. Here is a double beta refraction, respectively. The name speaks for itself. With this transformation of light, we get two rays, polarized again with different degrees, or one polarized, the other not polarized. And such polarization can be observed both in natural conditions, that is, in crystals that are formed in the Earth's crust, and in artificial environments, that is, manufactured glasses, liquids, solids, transparent, but most often under some kind of stress. It can be mechanical stress, that is, compression of this substance. It can be the action of an electric field, a magnetic field, and so on. Another way to polarize light is by passing it through some crystals. So let's take a little more detail about double melting and move on to the question of the course of rays in polarimeters. This means that a double ray of refraction is observed in the crystals of Icelandic spar, that is, a transparent crystal. A feature of this crystal is the ability to split the image. Look, the light passing through the crystal, well, almost equally clearly allows you to view the image, a doubled image, but at the same time, the image that turns out to be closer to the original is formed by so-called ordinary rays. As you can see, the distance from the beam direction, the previous beam direction to the so-called ordinary beam, is quite close. But the second image is obtained with the help of so-called extraordinary rays. Well, the singularity is due to the fact that it is polarized light. There are practically no differences for the human eye that an ordinary ray of the image is formed, which is unusual. Double refraction and refraction on some tourmaline crystals are caused by the interaction of a light wave with a substance. Moreover, these interactions are determined by isotherapy or isotherapy of the substance. That is, in isotropic homogeneous substances, the speed of propagation of a light beam is the same, so the direction that whatever direction the light beam chooses, it will propagate at the same speed, because it will meet the same number of, say, nodes to the historical lattice on its way. This will not affect the speed of propagation, the speed of movement of the substance, it will be preserved. But in low-level environments, environments in which the properties differ depending on the direction, that is, different densities, different distances between the nodes of the crystal lattice, different electromagnetic properties. The light wave will propagate at different speeds. That is, meeting on its way a larger number of particles with which this light wave will be forced to interact. Of course, there will be a slowdown in the propagation of light, and vice versa. The fewer such interactions, the faster, with greater speed, light propagates in a given direction. Well, it was decided to study in detail the prism of Nicholas. In physics, light is always currently polarized mainly with the help of polyroid films, as for the Nicholas prism. Well, perhaps the only thing you need, what kind of representation you need to get, is that this most transparent material, Icelandic spar, which is used to polarize light, is cut in a certain plane, and the place of the cut is then it sticks together again. But this transparent glue should have, look, a transparent glue should have a refractive index that falls into the gap between the refractive indices to which an ordinary and unusual ray reacts. In other words, the task of this gluing, and in particular glue, is to remove an ordinary ray from the field of view. Look at this. At the entrance we see a beam of natural light that falls on the Icelandic sword. At the exit we see a beam of polarized light. That's all. In other words, the purpose of such a device of the Nicholas prism is to isolate one of the two rays obtained by double refraction. Of course, the intensity of this beam is less than the intensity of the incident light, but the quality of this light is already somewhat different. That is, the order of these electromagnetic oscillations is higher. The relationship between the intensity of light, polarized light, that has passed through a tourmaline plate, with the intensity of light incident on this plate, was studied back in 1809th year by the mollusk, and in the picture that you see, the first crystal is just a crystal, with which polarized light is obtained. But then they emit polarized light. That is, starting from the point, so to speak, of the exit from the first crystal, the study of the behavior of the polarized beam begins. Here, it is a beam of polarized light passing through the second plate of tourmaline, that is, passing through another crystal that is capable of polarizing light. You can observe a decrease in the intensity of polarized light, because the intensity of polarized light is determined by the angle between the plane of polarization of this light. And the faces, well, not the faces more precisely, but the axis of the crystal in particular. I am interested in how far the plane of vibrations will be from the main axis of the crystal, the very axis in the direction of which the polarization of light occurred in the first case. Well, as an example, you can see in the picture an example of such a mechanistic approach to explaining the polarization of light. Look at the bottom picture first. So, if the rubber harness forces you to make an oscillatory movement, here in the direction of the screen plane again, then the obstacle there in the form of a slit, which will also be parallel to the screen, will not have, well, almost probably no effect if there is no discrepancy relative to the axis. But as soon as we start turning this transmission direction relative to the oscillations coinciding with the screen, we naturally extinguish these oscillations in this way. Extinguish the vibrations, mechanical vibrations of the rubber harness. Approximately the same thing happens when we consider the behavior of natural light and the passage of this light through polarizers, that is, through devices that are capable of transmitting light. The electromagnetic waves of which will oscillate in selected directions. If we put another polarizer in the path of the already polarized light, well, that is, conditionally another lattice, then with the help of this lattice we can find out whether the light is polarized or not. That is, it turns the polarizer at different angles relative to this transmitted light. We can see either completely transmitted light or some dimming. This is the property on which modern polyroid glasses and polyroid lenses are arranged there. We will not consider the passage of light through two polarizers in this picture. Let's go straight to the scheme of the passage of light rays in the saccharimeter. But before that, pay attention and remember. That saccharimetry is based on the phenomenon of rotation of the plane of polarization. The rotation of the plane of polarization consists in the ability of some substances to rotate the plane of polarization, that is, to rotate, to unfold in space, the oscillations of a vector, a light vector, provided that this medium is optically active. Not every medium interacts with light in this way. Some media simply heat up when light passes through it. Some, as I have already said, undergo some kind of chemical transformations. Here, and some media, interacting with light, change the direction of the plane of polarization. To optically active media, there are a number of environments related there. Let's first look at what an optically active medium is, and then move on to the direction of the rays in the saccharimeter. So, optically active media, or optically active substances, are divided into two types of substances. The first type, these are substances that do not lose their optical activity while in any of the aggregate states. That is, sugar in solution, sugar in pores, sugar in a crystal has optical activity. This very optical activity is due to the asymmetric structure of the molecules of this substance. Optically active substances of the second type acquire the properties of rotating the plane of polarization only when a number of conditions are met. For example, when there is a mechanical stress in any crystal, this area exposed to mechanical action becomes optically active. Well, or vice versa, it may be stretching. It can be an action, an external effect of an electric field, a magnetic field, well, in one way or another, naturally connected mainly with the structure. That is, the structure of the substance changes, its properties change. Well, now the course of the rays in the saccharimeter. So the saccharimeter is, well, or a polarimeter designed to measure the concentration of sugar. It is a tube like this, yes, but in laboratory work you will see a light bulb that is adjusted by turning the slots on this tube there. And then the light coming from the bulb passes through the first polarizer, that is, natural light is converted into polarized light. And then the polarized light, look, this is the chosen plane of polarization, and accordingly, the fluctuations of the vector E of the light vector. But then this selected plane, once in the optically active substance, begins to change its position. Well, the further the light passes and the longer the light interacts with the optically active substance, the more angle this light vector deviates. As a result, look, after passing through the cuvette, that is, through the optically active substance, the position of the vector E relative to the previous position, look, gives the angle alpha, the so-called angle of rotation of the polarization plane. It is this angle that the saccharimeter is able to measure. The measured angle, please note, is indicated by the letter alpha depends on L. L is the thickness of the cuvette layer, or this substance, depends on the concentration of the optically active substance, that is, on the concentration of sugar molecules. The more sugar there is in the urine or in the blood, the more the plane of polarization will turn around. And of course, the angle of rotation of the polarization plane depends on the so-called specific rotation. Specific rotation is a value that characterizes various optically active media. That is, for sugar alpha 0 is one value for cinnabar, for example. It is another for tartaric acids, the third, and so on. So, we looked at this with you. Well, pay attention to the Department of Chemistry. You have probably already studied the concept of a ration mixture. A concept that connects the so-called left and right rotating substances. These left-right rotating properties are properties that play a big role, for example, in pharmaceuticals. According to other physical properties, one substance is from another, that is, left rotating, which rotate the plane of polarization to the left, or right rotating, clockwise rotating vector, do not differ from each other. Well, for the most part, we are surrounded, of course, by racemic mixtures, mixtures that do not rotate the plane of polarization at all. This is due to the fact that these mixtures include both left and right rotating molecules in equal quantities. Well, here are 2 slides with examples. It's probably still a couple of minutes. So, polarimetry is a method that you will study in laboratory work. Yes, we have just looked at the basis of this method schematically with you. Well, that is, the greater the angle of rotation of the polarization plane, the correspondingly higher the concentration of the substance under study. The second direction is polarization microscopy. Look right away as an example. You have photos of crossed hair, children's hair visible here on the slide. Please note, in addition to the fact that the scaly structure, the volumetric structure of the hair is visible, it is clear that this hair is transparent. That is, here on the crossing of the hair. But it is clear that here the hair has, well, the object more precisely has one color, and here on the superimposition of one on the other, the light changes. That is, it is clear that inside it is a hollow structure, and the fact that it has a cylindrical shape, this is very clearly visible with an oppositional microscope. The third direction is the ability, with the help of this mechanical stress, to change the structure of an object, for example, a bone model or a model of some kind of dental structure, and as a result, well, let's say the model is made of plexiglass. As a result, the throughput of this substance changes, or rather, non-isotropic areas appear that interact with it in a different way, falling light. On the screen, we see either a darkening or, on the contrary, lighter areas that characterize the presence or absence of mechanical stress, and accordingly getting the conclusion that this particular area will be exposed to more impact. There is a greater risk of destruction of this structure. And finally, the polarizational glasses, which probably everyone uses, and every second one for sure. That's the peculiarity of these glasses, made of glass or with a polyroid film pasted on, is that, unlike ordinary colored sunglasses they do not change the color rendition. That is, they do not make the world pink there, or vice versa. They do not give some green shade of green there, more precisely. They do not give all shades of green to the world. They simply reduce the intensity of color. and this was used in particular by skiers, drivers, lovers of some water sports, because look, it is the reflected beam, that is a polarized beam. In order to compensate for the brightness of this polarized light, polyroid glasses are used, in which, well, it is unlikely that the main plane, that is, the plane that transmits polarized light, will coincide with the plane of oscillations of the polarized beam, the reflected polarized beam. That is, after all, there appears, well, at least some kind of image of the object to which the person is moving. Motorists also often use polyroids because these, in bright sunlight, light is also reflected from panels, plastic panels. So in order for these to be polarized light sources too, in order to compensate for these bright glare, they use polyroid glasses. Here, in the case of using just as dark glasses, we can also notice some polarization, anisotropy of some substances. For example, some pebbles on asphalt will look a little different if we look at them through real polyroids. By the way, real polyroids can also be checked using our phones. That is, when you rotate the glass relative to the screen of your phone, or, more precisely, the lens of a polyroid, you can see how the intensity of the image changes. If it changes well, it means it is a good polyroid. It can be used as a protection to protect your vision from the bright sun. In short, that's all I have. Thank you for your attention. This is where we stop.